Hello, everyone, and thank you very much for coming to our discussion for our MiniNet optical demonstration. Our system is SDN controlled dynamic front hall provisioning, and I will be showing the emulated virtual testbed simulation of our algorithm. So what our system looks like is it is a 4-node network showing data centers as well as residential and office areas, and it will be a 4-node, not a 6-node network like this. And we will be running a diurnal traffic pattern over the systems. Specifically, we will be running a residential diurnal traffic as well as an office area diurnal traffic demand system. And our topology, like I said, is a 4-node network that looks as so, where we have 90 transceivers on 90 channels. Our end nodes are radio units, and our central nodes, our end nodes are baseband units at data centers, and our central nodes R2 and R3 are radio unit aggregations that serve residential areas and serve office areas. With that said, let us start up um, our MiniNet optical topology and get our network up and running. Right now it's clearing stuff up and it's initializing the links. You'll notice that there are multiple ones that say S1 and T1. You will see in total 90 links between S1 and T1, S2 and T2, and so on. And you will see them very similar to how you saw them in the diagram that I showed earlier. I'll show them right now, but sadly as the system is loading, wonderful, I'm not usually able to show them, but since it's finished loading, so there are 90 links between S2 and T2 and T2 and R2, and the same is true for all of them. We will have 727 links in total in our system. With that, our MiniNet optical control line interface is up and running. Now, what you will see in our system is you will see a power spectrum monitoring window where you can see the signals incoming being turned on and that are being utilized by our system. And you will also see a light path provisioning graph, which we will provide at the end of the simulation. And it will show how many total light paths are in the system, how many are provisioned at 200G, 100G, and 50G, as well as underutilized. Now, the way we are able to generate it is with the following algorithm for our system. So as we discussed, we are modeling a metro network, and each of the signals are encoded on a 25 gigabit per second SIPRI stream that are made from radio units around aggregated ROADM units, and they are transmitted to baseband units at data centers. Ideally, we prefer to use the nearest data center, but we programmed it so that DC2 doesn't have enough capacity to handle the peak demand, and so at peak demand hours, it will be split between DC1, between this data center and this data center. And then our controller provisions the light paths, assigns data streams to the light path, and monitors the received GeoSNR in margins selected to that GeoSNR threshold. In other words, when the GeoSNR drops below a certain threshold, our SDN controller lowers the model data rate from 200 gigabit per second to 100 gigabit per second. And with that, and at the end of the hour, empty light paths that don't have any traffic will be torn down at the end. So with that, I will now start up the visualization system. And as you see, it's empty right now, but as it starts to run, the light paths will begin to occupy. And with that, I will now start our demo control system. and you can begin to see all these light paths now begin to occupy. Now it's worth taking a pause and seeing what is going on. So here we have a request that is made, but we need to install a light path to answer that. So we install a light path on channel 68 of the 90 that are available. We configure terminal T3 and T4 to transmit, and we then start configuring the OVS switch as well as the switch rules with OpenFlow, and this is those protocols being configured, and now it is up and running. So you can see now that we have a new system, we can start grooming CPRI traffic demands into our light paths. So here we have a request, and we can provision the light path successfully, so we can groom the traffic, and this is the OSNR and GOSNR of the system. And since this is most likely done at 200G, we have 7 that are occupied. We have one from when the system started up, and it says were able to install the traffic successfully, so that's 1. This is 2, 3, 4, 5, 6, 7, and 8. And now we have a new request, and we need to install a new light path. And at the beginning, we see this pattern quite a bit because we are just filling up we are turning on our network, so the requests are just coming in, and we are provisioning our light paths. However, as we go on, once they're fully provisioned and traffic starts being removed and can be added on, we can use the underutilized light paths that begin to show up. And let me see if I have an example of this in our code that I can find easily. We may need to scroll down for a bit to find some cases of that. So right now we're still going through a lot of the cases. We are still receiving new requests, and we are actually starting to now see light paths being underutilized, and so we are starting to tear down certain channels that do not have any traffic demands going on them. There's no new traffic in 3 and 4, just because the traffic demand is virtually the same and nothing needs to be tear down or added. We have more being removed, and now here you can see just a long chain of successful traffic requests. Even though we had a bunch teared down, we have a bunch of channels that are underutilized, and so we are just grooming our CPRI requests into the underutilized traffic. And so this is what you are seeing in the system. Now on the other hand, what you are seeing is you are seeing signals being received and turned on. So on our emulator, this shows the network, and this shows the transceivers and the switch rules being turned on and off and signals being received. So for example, you have T1 being turned on port 117, 146, 129, and you have the signal being received at 99, 176, 147, 129. However, there's some signals we were not able to route, so here we are saying unable to find a switch rule. So usually this means we have to try to reroute or find a new way to do so. So let's scroll down a little bit because our data is running out. So again, we have signals being turned on. We have switch rules we are unable to find. We have successful transmission. We have signals being turned on. Places where unsuccessful transmissions, several successful transmissions, and we are installing new switch rules to be able to respond to the traffic demands. So we have switch rules being installed, switch rules being uninstalled, and traffic demands being met. And this is what you will see all throughout the system. All the while, our system, as you can see, has occupied more and more with nodes. So this is really what we see for the discussion. And next we'll discuss the results for our light path provisioning system. So what we can see here is we see the traffic rates we see the traffic pattern over time. And the traffic is how many gigabits per second, as well as CPRI requests that are made from the BBU units. Now here our traffic load, both baseband units were easily able to answer the call of the nearest ROADM units. So we see a virtually identical image in both of these systems. However, one is in gigabits per second and the other is number of requests per hour. And so what we have also is how the wavelengths were provisioned, as well as the light paths of the system. On average, how many wavelengths do you have per every link, as well as how many total light paths you have per hour. Now, these are our light path provisioning results. And largely because our system was just going to the nearest ROADM, what we have is everything at 200, most of our system is at 200G utilization. And so every 200G system is able to handle 8 CPRI requests, because the CPRI requests are all at 25 gigabits per second. So there are some cases, however, where we don't need to use all the light paths, and therefore they become underutilized. Officially, an underutilized light path is a light path that is occupied with less than half of its total capacity. So as we said earlier, a 200G system can handle up to 8 CPRI requests. An underutilized light path is is a light path handling 4 or less of those requests. So this is why in periods right here where the traffic is rising, the number of underutilized light paths are dropping. But here, since more are being opened, you can see more light paths being open and underutilized. And areas where you have a drop, you have a rise in the underutilized light path. But places where the traffic is rising, the underutilized traffic is being occupied. And really, the CPRI requests the way the CPRI requests are answered is completely at random. The CPRI requests are groomed into the light paths more or less at random. And if we can find a light path available, we will groom the traffic demand in until we reach a certain level. And then after that, we will start utilizing we will start opening new paths, new light paths, in order for the data to be groomed in. And lastly, this is the total data flow in gigabits per second, where it maxes out around 25,000 gigabits per session, which is what we set the max traffic to be. So this is the type of data that you can receive from our this is the kind of data our system created. So thank you very much for our presentation, and I will hand it off to the next person.
Hello, I'm Jakayu. I will present this live demo for SDN-Controlled dynamic front-haul provisioning with Cosmos Testbed. As we mentioned before, this scenario is the wireless and optic converged networks in metro area. In left figure, you can see there are 6 locations. For wireless networks, each node is deployed with either baseband units or radio units. The wireless traffic data is transmitted between the radio units and the baseband units. And these 6 nodes can be classified as 3 types. the BBU nodes, office nodes, and residential nodes. The residential and the office nodes will follow the diurnal traffic patterns in the right figure. For the optical layer, each location is actually deployed with the ROADM. So the wireless data transmission is achieved by the separate data transmission between two ROADMs. So in this demo, I will present our designed SDN controller to dynamic provision light paths in Cosmos testbed with netconf and monitor the channel data. So this diagram shows the 4-node linear topology we built in Cosmos testbed. And when there's a wireless traffic data transmission request is sent to the optical layer. So the SDN controller will first try to find if there's a ready provisioned light path can handle this request. If there's no light path can handle this request, the SDN controller will set up a new light path. And if there's a light path without any separate data transmission, then the controller will remove this light path. So that is how the SDN dynamic can provision the light path. And then this figure shows the details of the Cosmos setup. The 4-node testbed, the 4-node setup is actually achieved by 6 Lumentum ROADMs. You can see for the middle 2 nodes, the bidirectional nodes, and each node is composed by 2 Lumentum ROADMs. And we use a common source to send 90 channel optic signals to each ROADM. And all the components, the common source, the fiber spool, and the Lumentum ROADMs are connected with a central Kellyan space switch. So right now I will go to a virtual machine in Cosmos, and it shows how the SDN controller runs and what we can get from the SDN controller. You can see right now we are running the SDN controller, and it shows the wavelength selective switch is configured. That is our ROADM. That is the ROADMs in the Cosmos are configured, and then for each light path, then we can get the channel ID and the light path ID, the channel frequency, the channel power, the channel port, and then and also the light path routes from ROADM 2 to ROADM 1. And then it's not straightforward. Then you can check the Lumentum GUI to see what we can have. You can see this is the Lumentum ROADM 2. Then we check the wavelength selective switch. Then we have all the light path information from light path 1 to light path 69. And what they have is like the channel ID, the channel frequency, if it's in service or out of service, the attenuation, the connection ports, and the power levels. Then we can collect those data and record the data and generate some plots. Then I wrote some simple script and to generate a plot and showing the channel power spectrum. You can see I'm plotting these figures. The horizontal x is the channel index. The vertical x is the power levels. So for ROADM 2, for the Lumentum ROADM 2, the channel power is ranging from -25 to -23 dB. So we can record all the channel information and know what's going on when we dynamic configure the light path. That is how we use the SDN controller to configure the Cosmos testbed. Thank you, everyone.